All right, let's jump into the next lecture. To me, this is when the class starts to get a little more exciting because um, or we start to get into, I guess, statistics rather than just sets and probability. So what I mean by statistics is things are going to start looking a little more like numbers, or we can imagine their connection to data a little more easily. So I want to introduce something called a random variable. A random variable we can think of as some number that we just haven't observed yet. It's going to result from an experiment. And so it could take any number of values, and it takes different values with different probabilities. To be more precise, um, well, this is another imprecise way of putting it. We have an experiment always happening in the background, and we know an experiment is going to result in some kind of outcome. A random variable is always a number, and it just is a number telling us about the outcome of the experiment. So here's how we officially define a random variable. Given a probability space, so remember omega is a sample space, B is a sigma algebra, that means a collection of subsets of the sample space to which we want to assign probabilities, and a probability function P which assigns those probabilities. So we have this setup, and remember the outcomes here might not be numeric. They could be like heads and tails, they could be blood types, they could be anything. They could also be numbers. But a random variable, x, we'll use x to denote a random variable, is a function which takes values in the sample space, that is outcomes, and it returns real numbers. So a random variable always takes real numbers. And this stuff seems kind of like a technicality. The important thing to remember is a random variable is a function which takes outcomes and gives us real numbers. This such that, this st means such that, this says the random variable has to, or this function that we're calling a random variable has to satisfy a property called measurability, which you'll learn about more when you take 8.10 and 8.11. So this looks at, it defines what we would call like the pre-image of a set. So imagine we have the sample space, and then we have a function x which takes outcomes in the sample space and gives us real numbers. So the real numbers, any number between minus infinity and infinity. And what we might, well, this tells us that for this to legitimately be called a random variable, what we need is for every set in the Borel sigma algebra of the real numbers, I need to have this property where if I imagine let's say I take the set A to B over here, which is a subset of the real numbers, and I could say it belongs to the Borel collection of subsets of the real numbers. If I have some interval, let's just say A to B, then x inverse of the set A to B is like all the omega which x carries to the interval AB. So this would be like all outcomes in the sample space such that my random variable x would be in the interval A to B. And what I need is for x to be a legitimate random variable, this set needs to belong to the original sigma algebra of my sample space. So for us in this course, this is going to be just some kind of technicality that we don't have to worry very much about. We can just think of a random variable as a function from the sample space to the real line. Okay. Um, let's define something called the support of a random variable. So as with any function, like x is carrying values from the sample space, outcomes in the sample space to real numbers, x might not be able to take any real numbered value. We'll see examples. But we're going to use this script x to denote the set of values that x can take. And we're going to call it the support of x. Okay, so let's look at this little example or set of examples. So let's, for each of these experiments, let's make the probability space and look at how x is defined and kind of look and see how it's a random variable. So number one, flip a coin and let x equal 1 if heads, 0 if tails. So here the experiment is like I could get heads or I could get tails. That's the sample space of the experiment, omega. And a reasonable sigma algebra for this experiment, for my sample space, would be like I can take any, all the subsets of omega, including omega itself. So take the empty set, take all of omega, take just h, take just t, and this is like the power set of omega. That's all subsets including omega itself. That can be our sigma algebra. And then the function p of omega, so little omega is going to come from here, is going to be like equal to 1/2 if omega is heads and 1/2 if omega is tails. All right, and so now I've got this random variable which is equal to 1 if omega is heads and 0 if omega is tails. Okay, so this is the way we can set up a random variable. Now, if we want to try to make sense of this kind of complicated looking condition, we might say, let's choose a set in the Borel sigma algebra on the real numbers. For example, let's just choose some interval, like let's choose the interval 1/2 up to 2. Then let me figure out what is the inverse image of the interval 1/2 up to 2 according to this random variable x. So this is going to be all the outcomes in the sample space such that x computed on that outcome is in the interval 1/2 up to 2. And so now I'm going to ask myself, for what values of omega in the sample space do I get a value of x between 1/2 and 2? Well, x can only take the values 0 and 1. So, and it takes the value 0 when I observe tails. It takes the value 1 when I observe heads. So this is just going to be heads. And I see that that is a set in my original sigma algebra. So it satisfies this condition, at least for that one interval 1/2 to 2. Now it's not really reasonable to like go through all Borel sets in the real numbers and check if that condition holds. This is just an example of like how do we interpret this pre-image of x. Let me make this neater. Let me also point out the support of x is 0, 1. So this thing we call the support of x, that's the number of values that it's not the number of values x can take, it's the set of values that x can take. So that's 0 and 1. So let me put this here. Let's look at the next one. So flip a coin 3 times and let x be the number of heads. So 2. So flip a coin 3 times and let x be the number of heads. So if I flip a coin 3 times, I can get these outcomes. Take a moment and write them down. T, T, H, T, H, T, H, T, T, and then H, H, H. Maybe makes sense to put it like this. So here's the sample space corresponding to the experiment. A sigma algebra for this would be like all, I'm just going to say all subsets of this, including this itself. I don't want to list them all, that would take too much time. And a probability for each one of these. They all have the same probability of happening. So there's 1, 2, 3, 4, 5, 6, 7, 8 of them. So 1/8 for all omega in omega. And my function x of omega looks like, let me grab some more paper here. My function x, which is my random variable, looks like what? X, uh-oh, what's going on here? Something very strange has happened. Let me go out of it and get back in. Let me open another one, get back into this one. Okay, things are back. Okay, so I'm counting the number of heads. That's my random variable. That's my numeric encoding of the experiment. So x could be 0, 1, 2, or 3. So I see the support of x is 0, 1, 2, or 3. And let's see, if I get tails, 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 that gives me 0. If I get tails, tails, heads, tails, heads, tails, heads, tails, tails, I get the value of 1. If I get heads, heads, tails, heads, tails, heads, tails, heads, heads, I get the value of 2 for x. And if I get all 3 heads, I can just say equals this outcome. If I get this one, I get 3. Okay. So just to practice this pre-image thing, look at, just to illustrate again what we mean by this, if I take some set, some interval in the real numbers, remember that this Borel sigma algebra on R is just like any sets of the form like A, B, or I could have closed endpoints and any countable unions or intersections of those sets. So just to illustrate this idea, take an interval, I don't know, let's take -1 up to 2. And let's look at we could call it the pre-image or x inverse of this set. This is all the omega, all the outcomes in the sample space, which would give me a value of my random variable in that interval. And so I see it's going to be these values in the sample space, or those outcomes, because I'm not including the endpoint 2, so I can't take those ones. So I'm going to get this one, this one, this one, and this one. those are all the outcomes in the sample space which the random variable x maps to the interval -1 to 2. And this belongs in the sigma algebra up here, all subsets of omega, including omega itself. Okay, so let's move on from there and look at the next thing. So we would like to make probability statements about our random variable x, which look like this. So I want to write like the probability that x is greater than 2, or the probability that x is less than 1, or like for any set A, which is like some interval in the real numbers, or anything in the Borel sigma algebra on R. We can just think of it as an interval on the real line. I want to write, I want to have an expression for the probability that my random variable falls in that interval. So we can think of this when we see all this Borel sigma algebra stuff. Just think, I want to have x in the interval a to b, or we could have square brackets, or open or close brackets. And the way we're going to define it is we're going to base it on our original probability function, which assigns probability to subsets of the sample space. So this here is the inverse of the set A. So it's like the outcomes in the sample space for which the random variable x gives us a value in A, and we're going to use our original probability function in our probability space to measure that probability. And that's how we're going to define our probability function for the random variable x. So if this A is like the interval a to b, I would say the probability that x is in the interval a to b is the probability that we get an outcome such that x computed on that outcome is in the interval a to b. Okay, so this p is like our original probability function defined on this collection of subsets of the sample space, and this px is this kind of new one that we're defining. Okay, so after a while we won't write this subset x anymore. We'll just understand what we mean when we write probability x in A. And if we think about this, we can understand that x is making basically a new probability space where R becomes the new sample space, since x always takes a value in the real numbers. And then we've got the Borel sigma algebra here and the new probability function based on x. So this all seems a little bit tedious, I'm sure, but you'll get into some of these details more next year. For us, we don't always need to pay attention to every level of nuance here. So we'll get into some examples. So this new function, this px, we often call it the probability distribution of x. So it basically tells us what values x is able to take, and it tells us how likely it takes each value. So let's try to describe this probability function, px, for a certain situation, for a certain probability space and random variable. So for rolling 2 dice, we have this probability space. We've kind of worked with it before. But then let's let x be the sum of the rolls. And let's describe this probability function for x by making a table containing these values. So for each value that our random variable x could take, that is in the support, I want to write down what's the probability that x takes that value. All right, so I think the easiest way to kind of describe the distribution, the probability distribution of x, is to first just write down the support. So if I'm rolling 2 dice and x is the sum of the rolls, I can get any of these numbers for the sum of the rolls. Okay, and so what I want to do is make a table where I've got all the values that x can take, 8, 9, 10, 11, and 12. And then down in the second row, I want to put the probability that x takes that value. So let's take, for example, probability that x equals 2. According to our definition of the probability function, I want to keep that there. What I need to do is go to my original probability function and take the probability of the set of outcomes for which x will be equal to 2. So this is going to be the probability of, now I've got to list the outcomes in the sample space which give me x equal to 2, and that is just going to be, I have to roll a 1 and a 1. And the probability of rolling a 1 and a 1 is 1 out of 36. So 1 out of 36. Then you move on to probability x equals 3. Let me not skip any details. This is omega in the sample space such that x of omega equals 3. So this is, and I could have written that up here too. So this is probability of the outcomes in the sample space such that x of the outcome is equal to 2. Like this. Okay, so coming down here, I'm going to get, I could roll a 1 and a 2 or a 2 and a 1. And the probability of that is 2 out of 36. And so on. If you go on to the next one, we're going to see a pattern here. This is going to be the outcomes such that x is equal to 4. And so I have to roll a 1 or a 3, or a 2 and a 2, or a 3 and a 1. So I get 3 out of 36. And so we find out that this is like 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36, and then it goes down 5, 4, 3, 2, 1, if you do it all out. All right, so this is how we can describe the probability distribution of this random variable. All right, good. So an important function associated with any random variable is what we call the cumulative distribution function, abbreviated CDF. The cumulative distribution function of a random variable, so I'm going to often write RV for random variable. The cumulative distribution function, we're going to denote it by capital F, x, of a random variable x is the function given by this. Okay, so the CDF tells us if I put in any specific value, lowercase x, it tells me the probability that my random variable x is less than or equal to that specific value. So specific value. And so this is let me emphasize, that's little x, this is big X. Big X is my random variable. It's a function from the sample space to the real numbers. And I have this probability function based on it. And so if I want to get what we call the CDF, I compute the probability that my random variable takes a value less than or equal to little x. And so this defines a function. Okay. So maybe you're thinking, how does it look like this? So you can write this as x belonging to the set minus infinity up to little x inclusive. Okay, and the function fx of little x is the one giving us these probabilities. So let's try to write down the CDF for this random variable, just to get a feel for what the CDF is. So the experiment is we're going to roll a die twice, and x is the number of times I get a 6. Okay. So I think the easiest way to begin working on the CDF is to go back to maybe describing the probability distribution like we did in this previous example. So let's figure out, first of all, the probability space. This is again like 1, 1, 1, 2, 2, 1, and so on. It's the sample space for rolling 2 dice. The sigma algebra will just be all subsets, and P of any set A is just going to be the number of outcomes in A divided by 36. So for all A in this sigma algebra, and X is equal to number of times I get a 6. So first of all, let's figure out the support of X. Number of times I get a 6. So it could be 0, 1, or 2. So what I should maybe first do is try to write down a table telling me what are the probabilities of these different values of x in the support. And then that's going to help me write down the cumulative distribution function. Okay, so let's figure out what is the probability that x equals 0. This is the probability that I get an outcome such that x on the outcome is 0. That means I get 0 6s. So if I make this table, I can get 1 to 6, 1 to 6. Let's see, I don't think I put a picture of the whole sample space here. If I write out like 1, 1, 1, 2, 2, 1, and so on, and make this whole table, I can see that rolls on which I get exactly 1 6 are these ones. So so here's where you get. So here's where you get 6 6. Here's where you'd have 6 1 up to 6 5. Here you'd have 1 6 to 5 6. So in these ones you get 1 6. In all of these ones you get 0 6s. And in this one you get 2 6s. So so this looks like 25 out of the 36 outcomes. So 25 are here, and then so I'm going to put 25 out of 36. And what about the probability that I get exactly 1 6? There's 5 here and there's 5 here, so that's going to be 10 out of 36, and then I get 2 6s with probability only 1 out of 36. Okay, so now how do I write down the CDF? Okay, so the CDF is a function which I have to define for every little x in the real numbers. So what we should think about is like the whole number line. Here's 0, here's 1, here's 2. If I put my little x right here, then probability that x is less than or equal to little x is going to be 0, because I can't get any x's down here. Okay, so let me say this: if x is less than 0, so if my little x is anywhere down here, then the probability of getting a value x or lower is going to be 0. But if I move x, like let's say x is exactly 0, now the probability that x is less than or equal to little x is going to be 25 over 36. If I put x here, I still have probability x less than or equal to little x is 25 out of 36. So I find that for any x equal to 0 or going up to 1 but not equal to 1, my probability is 25 over 36. But then if x is equal to 1 up to 2 but not equal to 2, then I've got, let's say x is up here, then the probability that my random variable is less than or equal to x is going to be the sum of these two probabilities. X could be 0 or x could be 1. So that's going to be the sum of these two, which is 35 over 36. And now if I put little x equal to 2, then I would sum all of these probabilities to get this probability that x is less than or equal to little x. And so I would get 36 over 36. And I would get that even if I put a little x greater than 2. So for all x greater than 2, it's going to be 36 over 36, which we know is equal to 1. So that's how we can write down a CDF, a cumulative distribution function, in a simple example. So let's, okay, so that was number 1. Let's draw a detailed picture of this. So I've got like 0, 1, 0, 1, and 2. Okay, so how could we draw a nice picture of this? This is a function which is equal to 0, but then when I reach 0, it goes up to 25 over 36. Let's say that's 25 over 36. And then it goes up to 35 over 36. And then it goes a little ways up to 1. So this here is 35 over 36. And this here is 25 over 36. So this is 1. Okay, if I wanted to put an axis there. Now, how should I put like where the endpoints are? So I should put it like this, because if I put in the value 0, it takes this value, 25 over 36, not this value. And same here, if I put in the value 1, it does not take the value 25 over 36, it takes the value 35 over 6. And here, if I put in the value 2, it's going to take 1 and not 35 over 36. So this, I could put these arrows, those go out to infinity. So that's how we would draw a picture of that CDF. Okay, so discuss interpretation of evaluating at 1/2. So, so here's, um, so here's 1/2, and so I find that if I evaluate this at 1/2, it means probability that x is less than or equal to 1/2. Now I know x can never take the value 1/2, but I get this 25 out of 36. So that's the height of the function at 1/2, and that means x takes values less than or equal to 1/2 with probability 25 over 36. That's because it can take the value 0 with that probability. So we see that the function has these jumps. The first jump is the probability that x is 0. So it jumps by that much. The second jump is the probability that x equals 1. The third jump is the probability that x equals 2. So we have that these jump sizes are just these numbers in our table, the probability with which x takes each value in its support. Okay, so I think we already did this. I should probably change that to 2. Okay, so we did that already. So whenever we write down a CDF, we need to define it for the whole real number line. Okay, so every random variable has a CDF. Not all of them look like this. We see this as like a step function. We'll come back to what that means in a little bit. Okay. We're going to talk a lot about CDFs. They're always going to be with us from now on. And so we need to be really familiar with a couple fundamentals about them. Every CDF has to have these 3 properties. And you can show that if a function has these 3 properties, there exists some random variable for which it is the CDF. We're going to show kind of this direction of this if and only if. If we begin with a CDF, we can show that it must have these 3 properties. So let's start with number 1. What name could we give to this property? This just means the function is non-decreasing. So if x is at least as big as, if y is at least as big as x, then f of y cannot be less than f of x. So it doesn't mean the function is always increasing, but it can go up, and then it can be flat, but it can never go down as we move from left to right. And we see that that's true of this. It never goes down as we move from left to right. So how can we prove that it's non-decreasing? So for if we take 2 values, x less than or equal to y, so little x less than or equal to little y, this is the probability that the random variable x is less than or equal to little x. And remember, this is the probability that, remember how we define our probability function in x. So this is the probability of the set of outcomes for which x is less than or equal to little x. And now I want to think about this little y. If I imagine the set of outcomes for which x is less than or equal to y, since y is greater than or equal to x, the set of outcomes for which x is less than or equal to little x must be contained inside this one. So this one is a subset of this one, because if I make this guy bigger, then I include potentially more outcomes of x. So remember, the probability function works like this. If I have a set A contained in the set B, it means probability of A is less than or equal to probability of B. So let me put that over here. So I can write less than or equal to probability of the set of outcomes for which my random variable is less than or equal to little y, because y is greater than or equal to x. And this is the probability that x is less than or equal to y. And that is the CDF evaluated at little y. So we've established this inequality right here. A CDF has to be non-decreasing. All right, let's look at number 2. Number 2 tells me that that if I send x down to negative infinity, the limit of my CDF has to be 0. And if I send x up to positive infinity, the limit of my CDF has to be 1. So we can look at this picture. So if I go to the left, my CDF goes down to 0, and if I move to the right, my CDF goes up to 1. In some cases, we get CDFs which have like an asymptote, maybe in both directions, and we'll see examples of that. So the limit going to the left has to be 0, and going to the right has to be 1. Let's figure out why that is the case. So let's take let's do this one first. So limit as x goes to infinity of this guy equals 1. So I want to show this. So we can choose any sequence, say xn. Let's make it an increasing sequence. Any increasing sequence xn such that the limit as n goes to infinity of xn is infinity. Then we can define sets, say an. We can do like this for n greater than or equal to 1. So maybe our sequence, I'll write it like this. So the idea is we have these sets where the upper endpoint is increasing, and what we notice about these is that they form an increasing sequence of sets. So n greater than or equal to 1 is an increasing sequence of sets. Okay, now what I can write is I can look at the limit as n goes to infinity of this, and if I can show that this is equal to 1, that's sufficient. So this is what I want to show, and I can show it by just saying for any increasing sequence xn, this is equal to 1. Okay. So what do we do? Let me write something like, we have this limit is equal to the limit n going to infinity of probability that x is less than or equal to little xn. So this is like x belonging to the set this. And so that is how we've defined our set an. And from here, like if I write x in an, that's limit. I can bring it back to my original probability function if I want by saying this is the set of outcomes in omega such that x omega is in an. And okay, so remember these sets make an increasing sequence of sets. And well, before we observe that, we learned, or we proved in the last section that for an increasing sequence of sets, the probability function is continuous. We know it's true in general that it's continuous, but we proved it for an increasing sequence of sets. So I can push the limit inside. And let me write out here, this is because of continuity of a probability function. That's what lets us push the limit inside. Oops. That lets us push the limit inside. Now, these sets, this is an increasing sequence of sets because an is contained in an plus 1, is contained in an plus 2, and so on. And I know we proved that the limit of an increasing sequence of sets is the union of the sets. N goes from 1 to infinity. Okay. So limit of increasing sequence of sets is the union. That's how we get to the next equality. Okay. And now if I consider the union of all of these, since these are nested and or they're an increasing sequence, if I imagine taking the union of all of these, I'm going to get out to the whole real number line. And so what I have in the end is just sample points such that I get a real valued x. So this is minus infinity to infinity, which is really the entire sample space, because x is always a real number. And so I get 1. Okay, so we can use basically the idea of continuity of the probability function to get here when we make this sequence of increasing sets. If I want to show that as x goes to minus infinity, this limits to 0, you can show this in a similar way. Similarly. Okay, you can show that similarly. Now, let's look at the third property. This is important. It looks a little bit strange. It says for any value x0 in the real numbers, if I take the limit of the function x coming from above down to x0, then I get x0. We're going to call this property right continuous. So the function needs to be right continuous. What does this mean? Imagine, so picture this function. If I, let's say I'm looking at this value right here, x0 equal to 2. If I'm standing right here, I like to draw a little man, and I'm taking the limit of the function as x approaches x2 from the left, the limit is 35 over 36, but the value of the function is 1. But if I take the limit starting above and going to the left, the limit of the function is 1, and the value of the function is also 1. So, so this function, this is what a right continuous function looks like. This is not a continuous function because it has these jumps, but it's right continuous because if I start above, so the limit starting above and going down to any point is the same as evaluating the function at that point. So if I take the limit going this way, it's the same as the value of the function at that point. If I start here and go this way, taking the limit, I get this value. But if I take the limit from below going up, I get this value, which is not equal to the value of the function. So remember, one way to think of continuity of a function is right hand and left hand limits are equal, and they're both equal to the value of the function. So we just need these right hand limits to be equal to the value of the function. And so every CDF, if it has jumps, they're going to look like this with respect to the endpoints. The upper part is always going to include the endpoint. Okay, so right continuous. How do we show that we have right continuity? So limit x goes down to x0 always needs to equal this. Okay, so the way we can show this is we can choose any sequence epsilon, and let's make it a decreasing sequence. Any decreasing sequence, so each one is less than the last, such that limit as n goes to infinity of epsilon equals 0. And then what we can do is set an can be the set minus infinity up to x0 plus epsilon n, so that I have an contains an plus 1, contains an plus 2. So we have a decreasing sequence of sets that we're going to work with. Now we can write limit as n goes to infinity of the CDF of x at x0 plus epsilon n is going to be the limit as n goes to infinity of the probability that my random variable x is less than or equal to x0 plus epsilon n, which using these sets A, I can just say probability that X lies in this set AN. And I've got this decreasing sequence. Let's see, let me go ahead and put, I'll go ahead and put omega. So this probability, probability that X is in the set AN is the original probability function for outcomes. It's all the outcomes such that my random variable gives me a value in the set AN. By continuity of probability functions, I can send the limit inside, and since this sequence is a decreasing sequence, I've got the intersection of all of these. So decreasing sequence of sets. N1 up to infinity. So it's the intersection of all of those. If I look at the intersection of all of these, it's going to wind up being outcomes such that X is less than or equal to X0. So only these outcomes belong in the intersection of all of these. Okay, so this is going to be just probability that the random variable X is less than or equal to X0, and that's the CDF of X evaluated at X0. So we see that by showing for any decreasing sequence of epsilons with limit 0, this limit is equal to f of x at x0, which shows what we wanted to show. So we have this property of right continuity for any CDF. Okay. Now, let's see. I'm gonna skip that one for now. So let's look at how the CDF allows us to categorize random variables as either continuous or discrete random variables. So every random variable in the universe has a CDF. And we say that a random variable is continuous if the CDF is a continuous function. So we haven't seen examples of a totally continuous CDF yet, but we will. And we call a random variable discrete if the CDF is a step function. We've seen that already. So this up here, this is a step function. So this means X is a discrete random variable. And if we had a continuous CDF, we would call the random variable a continuous random variable. We can have random variables which are kind of a mixture of the two. So if we just look at these three properties that every CDF must possess, it allows for more than just step functions and totally continuous functions. So a step function is like this, for example. So we have step, or you could have a continuous one. You could also have some kind of combination. So notice that this is this would still satisfy everything. It's non-decreasing. It limits to 1, limits to 0 going in that direction, and it's right continuous. So I can, if I take the right hand limit, the value of the function at the limit is equal to the limit. So it satisfies this property. Most often we deal with either totally discrete random variables or continuous. So I'll put discrete there, but you can have a mixture of the two. Okay, so let's end by talking about one more important fact about continuous random variables. So we're going to discuss an important fact about continuous random variables. We haven't really looked at any example of one yet, but it turns out that if x is continuous, where we call it continuous if the CDF is continuous, then the probability that the random variable x takes any specific value has to be equal to 0 for all little x, so for any specific value. This is a consequence of our definition of a continuous random variable right here. Okay, so how do we know that? So let's go ahead and show it. So we're gonna choose any sequence of epsilons going down to 0. So these are positive epsilons, and they're decreasing sequence, and their limit is 0. Then we can write that the set containing just x is contained in the interval x minus epsilon n up to x for all n greater than or equal to 1. So I can write in consequence that the probability that x equals little x is less than or equal to the probability that x belongs to this interval. Okay, because it's this idea that if A is contained in B, it means probability of A is less than or equal to probability of B. That's where that comes from. Now, what I can write here, if we think about it, you might want to write it out in a few more steps, but we see that I can take the CDF evaluated at this upper value and subtract the CDF at this lower value. So imagine here's x minus epsilon n, here's x, we have some CDF, and the height here is probability that x is less than or equal to little x. The height here is probability that x is less than or equal to x minus epsilon n. And so the difference fx at x minus fx at x minus epsilon n, this is the probability that x lies in this interval between. So x minus epsilon n up to x. Epsilon n up to x. Okay, so that's why I wrote this. So having observed that, then we can write, remember I'm trying to show that this is actually equal to 0 for all x in the case where I have a continuous CDF. I can write this because probabilities are always non-negative, and I can say that what I'm going to do is kind of squish this down to 0. So I know it's greater than or equal to 0, and I'm going to write over here something that's less than or equal to, and I'm going to show that this thing is going to go to 0. Or that I'm going to show that this right-hand side is equal to 0. So remember, I've got this is bounded above by this, so it must also be bounded above by the limit of this. So this is for all n, and if this inequality holds for all n, then it also holds for the limit of the right-hand side. So I can put limit of fx minus fx x minus epsilon n. And if I take this limit, it passes by the first one, and then I've got limit n goes to infinity of the CDF evaluated at x minus epsilon n. Since I have a continuous CDF, I can pass the limit inside. That's by the definition of continuity. So continuity means I can pass the limit inside. And if I take this limit, I've said that my sequence epsilon n goes to 0. So this is the CDF at little x minus the CDF at little x, which is 0. So I've said that this probability is greater than or equal to 0, and it's also less than or equal to 0. That means it's equal to 0. All right. So when I have a continuous random variable, which a continuous random variable just means its CDF is continuous, it means that the probability that it takes any specific value is going to be 0. And we'll see examples of that, and we'll understand why that makes intuitive sense as well. So the idea is, like, if I push these closer and closer together, then and I don't have any jump in the CDF, then eventually the difference between these two probabilities is going to go down to 0. But if I have a jump in the CDF, like in this one, if I have a jump, then if I am going this way and going this way, I'm still going to be left with this jump in here. And so, so for a discrete random variable, you have positive probabilities for single points. Okay, we're gonna finish it up right there. Well, let's just do this final kind of silly example. Here's an example of like a continuous CDF. Okay, so let's let the random variable x be months until you drop your new phone. Maybe you drop it and get a crack in the screen. And suppose x has the CDF given by this function. Okay, so let's check whether this CDF has the three properties of a CDF. And maybe we could also ask, is x a continuous or discrete? I think maybe the best way to do this is let's just draw a picture of the first one instead of going into all the details rigorously. So here's 0, and it looks like when x is less than 0, the CDF just takes the value 0. But then at 0, if I plug in x equals 0, I get 1 minus 1 minus e to the 0, so 1 minus 1. So it kind of goes, we find that it goes up like this, and it has an asymptote at 1. Okay, so here's the function 1 minus e to the minus x over 10. for x greater than 0 and 0 for x less than 0. Okay, it's continuous. So we have a continuous random variable. But let's look at these three properties. Is it non-decreasing? That was the first one. Non-decreasing. Yes, it's non-decreasing. So it never goes down as we move from left to right. Do we have that when I go to the left, oops, if I send x down to negative infinity, I'm supposed to get 0. Yeah, that checks out. And if I take the limit x goes to positive infinity, it limits to 1. So that's true as well. And then the third one was this right continuity property, which said if I take this limit, I should get, if I take this right-hand limit, it should equal the endpoint. This is true because the function is totally continuous. So continuity, well, let me say continuous implies right continuous. Okay, if it's totally continuous, like this function is, then it's always right continuous. Okay, because the definition of being continuous means this property of right continuity. It means this holds in both directions. Okay, so we're going to wrap this lecture up next time. Okay, so we're done for today.